Hi again. We'll continue our work on actuarial mathematics, building our understanding step by step. So at this moment, we will jump into evaluating the actuarially present value, actuarial present value. So just as to understand what I mean by actuarial present value, let's go back to interest theory. In interest theory, if let's say somebody age X and X plus T promised to get an amount of money, we usually get this value here. We use a present value, and the assumption here that this payment is certain. It's for sure the individual will get that payment, right? So like the payment is certain, so all we need to do is we discount it back. In actuarial mathematics here, what we will see is not like that certain. So same logic here. Somebody at age X plus T is promised to receive benefit contingent on an event to happen. So this is contingent payment. What do I mean by contingent payment? It's conditional, for instance, on death. So if it's conditional on death, which is life insurance, so there is no payment if the individual is alive, but there is a payment if the individual passes away. So it will go to his or her estate. So we need to discount it back here. Is we use the actuarial present value. Right? So we're moving from here interest theory to here actuarial. So the very same logic, there is not much of a difference here, is that the actuarial present value, you take the present value, which is from the interest theory, right? The same present value from interest theory, and then you multiply it, and this is very important, with a probability. And the probability of the event that we are making our payment contingent on. Just let's take a quick example. It should be straightforward, not really complicated area. If we take one example, let's say an individual, I said life insurance that at death, but let's take not life insurance. Let's take somebody age alive, age 60. So this individual will receive, part of the package for employment package will receive a payment. PMT, I usually use PMT for payment. So we'll receive a payment equal to, let's say, $10,000 upon retirement. First one, let's calculate the present value of this payment. Present value. So we want to calculate the present value. It's simple. Let's say let's assume that I is 5%. So if I is 5%, present value, we take the 10,000 divided by 105 raised to 5, right? So I use my calculator. So 1.5 raised to minus 5 multiplied by 10,000. Of course, you can write it also 10,000 multiplied by V to 5. Same logic, right? So I got 7835.26. This is the present value. The second question is how we can calculate what you need to calculate actuarial present value. We need a probability. And what kind of probability here is, remember that upon retirement. So he needs to survive till retirement to get the benefit, right? So if he survive, maybe we should clarify upon retirement. Now, if payment is conditional, or if maybe we can write it here, if he or she survives to age 65, right? So it's conditional on survival. So we'll get nothing if the individual did not survive. So we need to compute. The question is actuarial present value. we need probability, and probability can be different probability, but for our question here of surviving, let's say it's in actuarial math P 5P 460, an individual age 5 survive, and this is small p, right, survive to age 60. Let's say it's given to us P 65 is, let's say it's given to us 0.9. Then the actuarial present value, we can write it in different way, is the expected value of the present value. So the actuarial present value is the expected value of the present value, the expected. And how we calculate the expected? We multiply it by probability. What is the expected value of getting ahead? Is you multiply the probability by the head, and you get it. The same logic. So you multiply x by the number of trials. If you do 10 times, so n multiplied by the probability of success, you get the expected value. The same logic here. So we need the present value multiplied by probability. We already calculated it, 7835.26 multiplied by 0.9. I still have it on my calculator, so I can quickly calculate it. It's 7051.735. Right, it should be, of course, less than the like the maximum value for this one is certain, if certain the individual to live. So this should be less than this one. Right? It should make sense. It's nothing complicated here. So the point here for actuarial value and for present, let's summarize. Actuarial present value is the expected of the present value. Right? So let's take, now get into our model here. So we're looking at life insurance here. Life insurance, the same logic. A life is X. So we'll receive a payment. We'll receive usually called the payment BT, or I call it sometimes payment PMT. So we'll receive in the future upon death. Right? So this one will get it back into here, actuarial present value. So it's one benefit upon death, right? So this one is called whole life insurance. And the word whole life insurance is because it's unbounded up, for the whole life. Later on, we'll take a term life insurance. So it's not until, for the rest of the life, but it might be only you get insurance for 10 years. So when I was working in a few I was working for the United Nations, so I worked in a dangerous zone. So I would take term insurance, look for the 2 years that I'm assigned to those hardship duty station. So only for them. That is, we'll discuss it later. But for now, we'll look at whole life insurance. So for the whole life. And we'll make it also payable. We'll make it also payable at time of death. So we'll make this this insurance payable at time of death. And it's very important to read carefully what the question, because at time of death here it tells us it's continuous. Because also we can think of insurance that it's paid at the end of the month that the death occurs, or at the end of the year. But here it's time of death, and that is, we can call it continuous also. It's not discrete at time of death. The actuarial notation for this one, and this is, we need to be careful here. For any benefit, insurance benefit, we use the notation A, capital A. For insurance benefit, it's always we use the notation A, right? As the standard by now, there is logic. You're gonna see lots of notations now, but there is logic for these notations. You shouldn't be overwhelmed because there is a logic. So A is the letter that is assigned for, again, the insurance benefit. And X, by now you know that, it's the age. and we will have a bar here, and this is for the continuous. So this is age, and this is to say it's continuous. Like the payment occurs at time of death. Maybe not just let me make it a clearer, payable at T, time of death. And this we give it by the bar here. So it's A capital, subscript X, it's for the age, and the bar is to say it's continuous. And A of X, how we calculate it, it's expected value of the present value. But what is the present value? Present value of a payment is VT, right? Or equal, you can think of it delta T. Right? This is the present value. We start with $1, right? Usually we start whole life insurance, it's $1, and later on we can alter it to any other payment. So PT. So the expected value of PV, which is expected value of E minus lambda T, is equal. And this is continuous case, right? In continuous case, we know that we need to use integration from 0 to infinity, because the whole life, why we have it to infinity is the whole life. And then what you need to have is, you have your value here, lambda T, you multiply it by f of t, dt, right? You can think about it also, again, A of X is, again, the expected value. You can write it also 0 to infinity, E minus lambda T. F of t can be written t from last time, tpx mu x plus t dt. Right? You can write it in either way. So maybe I should write it carefully. tpx mu x plus t, right? dt. Any form of this can be okay, right? It's the same logic, but it's just, we need to remember it's the expected value of the present value. Let's take one example, it helps us to understand. But before that, just also maybe I should introduce another notation here before of that, right? This is what we will be dealing with, or it can be written in this form. Now, in insurance, this is the actuarially expected value. This is on average, this is the cost. But if you work in the industry, usually they take a variation, you know, like a measure for variation, or the variance you take. Why? Because for risk management. For risk management, you need to know what is the variance, because this is the average, the actuarially balanced value, but it can fluctuate. So usually take a measurement, or you do calculate the standard deviation or the variance, so you can do risk management approach to reduce risk. So we need to calculate the variance of the present value. Right? Or usually we call this present value, we have another term to it, Z. So the variance of this payment, Z is the payment. You can use also, or expected value of Z here. Another term just to simplify a little bit. The variance of the whole life insurance payment is, we need to calculate it. Remember, it's the same logic. It's we need, this one is AX bar minus. Now we need the second moment. Or the expected value of Z to 2, which is here expected value of Z to 2. And this is to say here it's raised to 2. Right? This is the definition of variance. Now let's take the expected value of Z2 separately. This, it has a notation, actuarial notation is A X. The same thing here, but because the second moment you have superscript here too on top, right? And this is the new notation here. The addition one is to say second moment. Right? So the 2 here, it tells us the second moment. So let's calculate it. Is you have e minus lambda t, which is your z, you raise it to 2, then multiply by f t dt. You can also from 0 to infinity, because this is whole life, 0 to infinity, you can write it also 0 to infinity. Now this can be e minus lambda t, oh sorry, e minus 2 lambda t, e minus 2 lambda t, and t p x mu x plus t dt. Right, this is another one here. We can, what you can recognize is exactly the same one here, but you used new lambda, new delta, I mean, the interest, force of interest is double that. So it's the same one using the double force of interest. So variance of z, then it becomes ax2 minus ax bar everything raised to 2. Let's take one example. Right. And this kind of things, you I would imagine by now you should develop your formula sheet, so you summarize these formulas so you can always come back to them. Too many notations, but these notations, if you get the logic, you will be okay. There is a logic for these notations, so they repeat it but with different letters, but there is logic to it. Excuse me. Let's take one example. The two common distributions that we always look at, one is uniform, the other one is we look at also exponential distribution. Let's look at first uniform. So let's say remaining lifetime So we look at remaining, my handwriting is getting worse. Remaining lifetime is uniform, or maybe we can write it is around, just to define it, it's a random variable. So remaining lifetime is a random variable, is a random variable, or maybe a uniform random variable, or as a uniform random variable over, let's take the general form. So the remaining lifetime at birth is a random variable over 0 to omega, right? 0 to omega. So we need to calculate and we need to find a general expression for ax and 2ax. Right, so we need to find the expected value of the present value of the insurance, or the whole life insurance, this one, and 2a bar x. So we need to find the whole life in and like a general form. And this is very important because many questions you don't need to integrate all the time. It's just if you know the formula, calculate it quickly. So remember, ax, it's the expected value, right? So it's the expected value. We know the expected value of the present value. What's the present value? It's e minus lambda t. So multiply it by the it's f of t dt, or tpx mu x plus 2. And we know for uniform, now this is age x, it's not age 0. Remember, let's draw it here. This is 0. This is age x, small x, and this is omega here, right? So we are here, we're looking at ax here, not at 0. So what's remaining lifetime here is not omega, it's omega minus x, right? Because we're not looking at a0, we're looking at ax, right? So just remember this one. So as I mentioned, so ft, the remaining lifetime here is uniformly distributed over 1 over omega over x, over omega minus x. Right, so it will be ft, if you recall what we did last time, is omega over x, right, for this one. Because uniformly distributed and we are here. So the rest is uniformly distributed. So now if we know this fact, this is, we've done it before, is then this one become from 0. We don't have to infinity, we have to omega. But we are here, right? We already here. So t is from 0 because we are here to, instead of omega, omega minus x. Now we have e minus lambda t, right? E minus lambda t, this is the present value multiplied by 1 over omega minus x omega minus x, yeah, dt. Remember the here the x is a constant, it's a number, you know. Let's say age 30, age 40, this is a constant, so the whole thing is constant. So if you do little bit of manipulation here, what you will find, the general form for this one is actually easy. You just take this constant outside and you integrate this one. What you will have is that this one is omega minus x multiplied by annuity certain omega minus x. This is something you really need to memorize. It's very important relationship, right? You expect many questions related to using this formula, right? And what is this? Just to remind us, is annuity certain. So we take the annuity certain and we divide it by omega minus x. So same logic. If you have ax 2 bar, remember this is the same thing, but you change delta, the force of interest, which you multiply it by 2. And this should be the same one, omega minus x, multiplied by the same one, omega minus x. But what you need to see is you use 2 lambda, evaluated with 2 delta, like 2 forces of interest. So you take 1 over omega minus x, and then you multiply it by the annuity certain, and this annuity certain is 2 delta, right? Let's take one example, but just recall in case you forgot. Annuity certain of n is equal 1 minus e minus lambda n divided by delta, right? This is just recall, this is there is nothing actuarial here, it's annuity certain. These two formulas are very important, right? Let's take one example how we can, let's take one example. So the example we look at, let's say remaining lifetime is uniformly distributed. Let's say remaining lifetime, or T, is uniformly distributed with omega equal let's say 100. So it's uniformly distributed between 0 and 100. Let's say random variable, just random, not to confuse you, at birth, or life random variable at birth is with omega. So this is between 0 and 100. Now we want to find, let's say for age 30, we want to find A30. And then we need to find the variance. Like, let's draw what we are looking here. This is time 0, this is time 100. We reach the age 30, so we wanted to evaluate A30 here, right? So the remaining lifetime here, it becomes omega minus x, which is 70, right? And now it's easy. All we need to do is A bar 30 is 1 over omega minus, if we go back to this formula, right? 1 omega minus x and certain, right? So it's 1 omega minus x is 70 multiplied by a 70. And what is the 70 here? Just to remind you, omega minus x, and this is the same. And this is so easy, right? It's all we need to do is 1 over 70 multiplied by 1 minus e point. Let's make, did I make, what is, yeah, we need to have delta. Let's say delta is, let's make it 5%, right? Or maybe, yeah, let's do it 5%. Given that delta is 5%, right? 0.5 multiplied by 70 divided by 0.5. Usually my calculator, in one step I calculate it, I usually use the same calculator as I mentioned, so it helps me the more I practice. So it's 1 minus e raised to minus 0.5 multiplied by 70 divided by 0.5, then I divide it again by 70. So the value of the insurance is, I got to be 27, right, just to see it. 2771. What does that mean? It means if somebody age 30 with this life or this life distribution or mortality distribution, this individual, to get an insurance, unit insurance of $1, to get $1 at time of death, he or she, the actuarial balance value, they need to pay 27 cents for each 1 unit of insurance. So if they insure for 100,000, so they will pay 27,000 to get this insurance. Again, this is uniformly distributed, which is not logical in human life, right? So this is like for insurance purpose for age 30. Now, what if you want to calculate A30, the same one, too? Same logic, there is nothing changed. 1 over 70 and multiply by 1 minus e. Instead of 0.5, then we multiply minus 0, 1, 0, 70 divided by 0.10. Want you to see here, and this is 2 times delta. Here is delta, right? Do you see the logic here? All you need to do for the second moment is you multiply delta by this. That's why it's important to memorize this formula, because then you don't need to keep calculating it. So if you calculate this one, all you need to do is take this one, now make it 1, 0, divided by 0.1, divided by 70. I got it to be 14%. So the second moment is 0.14273. Now variance, because it's important to calculate variance of z, is 2ax minus ax bar everything raised to 2. So this is 0.14273 minus our friend here 0.2771 raised to 2. So all I need to do is I keep it in my calculator, so I immediately can compute it. So I get this value, should be able to get this value, 6594. Right. So the variance 659. Right. This is straightforward, it's easy, nothing complicated. So wanted you again to memorize these formulas for the for this and this, very important. Now the second important distribution, as you know, we've been talking so much about it, is exponential distribution. We used it a lot. So example. Now let's say t is, t is remaining lifetime, is exponentially distributed. So it's exponentially distributed with mu, right? And this is mu with, sorry, let me write it here, distributed with mu, right? Mu is the mortality rate. That's mu, the mortality rate. Now AX, remember, it's the expected value of Z, which is E minus lambda t. So how we calculate the expected value from 0 to infinity? Exponential distribution is not bounded, 0 to infinity, right? And this is whole life, so from 0 to whole life. But in uniform distribution, you have omega, you have limit. Here we don't have limit. From 0 to infinity, you take the payment here, which is E minus delta t. We need to multiply it by ft dt, or this is in tpx mu x, right? And this is, if you recall, in uniform distribution, E minus delta t, and this one ft is mu multiplied by E minus mu t dt. This is the definition, whether it's mu x, which is mu constant force of mortality, and mu t tpx, right? So now this is easy to integrate because this is constant, right? And well, you can simplify it first into E minus, you add the lambda plus mu, delta plus mu t, and you have left mu dt. If you integrate it, you would get this nice formula. It's very easy, right? You take this one in the denominator. It's very easy, so we've done it before, so it will get in mu plus delta. So AX, the expected value of this one here, is AX. Okay. So we wanted to calculate for uniform distribution is AX is t. But I want you to recognize here you don't have any x, so it doesn't matter the age, and remember exponential distribution is memoryless. So regardless the age, always the value of the insurance will be this. And if you do the second moment as well for risk management purpose, it would be mu, but same thing mu, but instead of delta you have 2 delta. And variance is variance, right? Is AX2 minus AX, same, always the same, right? And those are very important to memorize. We expect to see many questions related to this. It's really not difficult here. Let's take one example also to make sure that we understand this distribution. Let's take example here. And this is the beauty about it, there's no x, it's easy to compute. So example is t remaining lifetime is exponential distribution, distributed with mu, the force of mortality is, let's make it 0.5%, and force of interest here, delta, is, let's make it 10%. Now we want to calculate expected value of an insured, expected insurance, the whole insurance value for the payable at time of death for an individual currently age 30. So an insured enter this insurance at age 30 and expected to be paid $1 unit of insurance at time of death, right? At the moment of death, because it's continuous. It's so easy. It has nothing if somebody 30 or 100. It's the same value of insurance. So it will be mu over mu plus delta, which is 0.5 divided by 0.5 plus 0.10. 1 over 5 over 15, which is 1 over 3. If you want to calculate the second moment, it's mu plus 2 delta 0.5, and this is where many mistakes are made, is sometimes you multiply mu by 2, not delta. So we need to be careful. What's multiplied by 2 is delta. Right, because we multiplied by 2. So this will be 5 over 25, 1/5. If you want variance now of z, which is, as we discussed, 2ax, our x is 30 for h 30, minus a bar 30 raised to 2, everything here, is equal to 1/5 minus 1/3, we raise it to 2, so 1/5 so if you multiply it by so it's 1/5, I mean 1/5 minus 1/9, so it will be 9/5 45, and then 9 minus 5 will be 4. So this is the insurance for this one, right? It's easy. But now what you recognize here, what we calculated is the value of the payment is $1, right? We looked at age x at x plus t. We looked at if death occurs, or let's say in the general case, there is $1 paid at time of death. Now what if you wanted to calculate it not $1, $1,000 or any value? Let's call it B. We usually call it B. The payment, not $1. It's simple. So what is the expected value of Z here? Which is expected value of B minus delta T. Remember, this is the expected value of present value. What's the expected value, or the actuarially present value? Also, we can use all those notation, right? Because this one can be from 0 to infinity, B E minus delta T TPX mu x plus T dt, right? TPX mu x plus T dt, right? We can take the B outside here, so it becomes like B A X, right? So always if there is a payment, or a benefit amount other than $1, the benefit amount can be multiplied by the actuarial value of $1, the whole life insurance. But for second moment, expected value of present value Z to 2, let's say, this will be B to 2, right? It's similar to any value here, because you get it out, it will be squared. The constant, you will get it out. So will be B2 A2 bar X, this way, and you can continue the calculation. So the standard is to calculate it for $1, and after you calculate for $1, you can multiply by whatever value you wanted. So this whole insurance, next time we'll look at also term insurance. Instead of, as I mentioned, having insurance until forever, you have a term insurance for a specific number of years, for 5 years, 2 years. Somebody is assigned to go to an assignment in certain work, or work for employment for 2 years. They give him life insurance or her life insurance. So for that term, then we'll look at it as we move on.